We are in a very remote environment. It's a harsh environment. You move slower, you're tired, your eyes hurt because it is so bright out there. You're cold, you can't remember the last time you were warm. And to, kind of make matters worse, you're digging giant holes in the snow. So you're working hard the whole time that all of these elements are just pounding on you.
The SnowX project is really a multi-year campaign to test different instruments and techniques for observing snow characteristics in different regions and different snow types. So we collect measurements on the ground with different ground-based instruments and observing techniques. We use that to validate instruments on aircraft and in the air, and eventually, hopefully, get some instrument on a satellite.
One of the advantages of Grand Mesa is its elevation. We're at over 10,000 feet here, and so as you can see, the snow is not wet at all. And so we want to start by really proving the concept in dry snow. A lot of the remote sensing approaches are also challenged by complex topography, so really steep topography. And as you can see, where we're standing here, we're on the top of a mesa, which is relatively flat. This is the largest mesa in the world, and so it's a pretty unique spot to do this work.
Within the pits, we're looking at the vertical stratigraphy, so the layering of the snowpack and the different characteristics of those layers, temperature, density.
I'm operating the snow micropenetrometer, which is one instrument that they use in the pit crews to look at the hardness of the snow and to look at the microstructure.
The microstructure is a very, very important characteristic for these active passive microwave retrievals, so we wanted to get that in a lot of locations.
I've just done a radar survey in a particular way, and we use this type of sampling strategy. We're calling it a Heimstra spiral. It's a spiral pattern. I'm making 100 measurements per second as I drive the snowmobile, and that is a very similar measurement to what's happening on the aircraft.
SWISAR really stands for Snow Water Equivalent Synthetic Aperture Radar and Radiometer, and it's actually two instruments in one. It has an active radar and a passive radiometer. Basically, they both work on the microwave frequencies, and what they do is to penetrate the snowpack a little bit and give us the volume scattering information, then which we can relate to how much water is inside the snowpack.
Snow water equivalent is really the volume of water that's stored in the snowpack. For hydrologic applications, that's really the most important characteristic. We want to know how much is available to melt and where it's going to go, evaporate into our groundwater reservoirs, and how much is available.
Our climate's also changing, and snow is playing a really big role in that. And it's a big piece of the hydrologic cycle that's quite uncertain, and it's one of the pieces that we really see as a very high priority to get more quantitative, more accurate estimates for.
Snow is a really important part of our planet. It provides water, hydropower. It's a water source for agriculture and water supply.
When we have snow in our mountains, it's holding it and it's kind of like timing the melt in like a slow release versus just an onset of rain or a flood event.
As we build these records for longer time series, we would be able to tell how the snow accumulation is changing over a given area and how that might impact the agriculture in that area or how the people live in that area.
I'm really excited about the potential right now. I think there's a lot of excitement in the snow community. There's a lot of collaboration. I think we really are at a point where we can push the science forward and move towards a global snow product and a satellite mission, hopefully.